Hi guys, today we're gonna explain about
how a current carrying conductor generates magnetic field. There are three of it, which is long straight, circular coil, solenoid, current carrying conductor.
a long straight conductor carrying an electric current generates magnetic fields around it. The magnetic fields in the shape of concentric circles centered on the wire and lying in the planes perpendicular to its length. The direction of the magnetic fields can be determined by using a right-hand grip rule. If you grasp your wire with your right hand, with your thumb pointing in the direction of the current flow, your finger will curl in the direction of the magnetic fields line. The strength of these magnetic fields can be determined by the equations. These relationships indicate that increasing the current will straighten the magnetic fields, and the magnetic fields get weaker as you go further away from the current carrying conductor.
So by looking at the previous explanation about long straight current carrying conductor, this can be turned into circular coil carrying conductor. Let's take a look at it.
By using right-hand grip rule, we can see as the current is going up, the magnetic field points toward the anti-clockwise direction. Meanwhile, as it is pointing downward, it is in clockwise direction. Within the space enclosed by the coil, the lines of force are in the same direction, and it is the strongest magnetic field.
Curl your finger along the current direction and point your thumb towards the magnetic field which is the strongest at the center of the coil. The field lines form circular loops around the wire and combine at the center to create a strong magnetic field, just like the bar magnet. The strength of the field at the center can be calculated by this formula. And that's how a simple coil generates a magnetic field.
Now, what will happen to the magnetic field if you have a lot of circular coil forming a solenoid? You will also be using the right hand grip rule. Now, curl your right hand fingers around the solenoid in the direction of the current flow. Your thumb will point in the direction of the magnetic field inside the solenoid. Inside the solenoid, the field is nearly uniform and directed along the solenoid's axis. Outside the solenoid, the field lines is spreading out and form a weaker field, resembling the field of a bar magnet. The solenoid thus behaves like a magnet, with one end acting as a north pole and the other one as a south pole. The strength of the magnetic field can be determined by using this formula.